Please help me welcome Matthew and Stephen to the stage.
Hello, everyone, and welcome. Thanks for coming to ModCon. We are super excited to give you a little deeper dive into some of the things we announced this morning about Max. In particular, we're going to dive into the extensibility aspect of this. But first, a little bit of bookkeeping. We'll give a quick overview of Max, talk about how people can customize models today, and then talk about what we've been building to really make extensibility in Max a real thing. So Max is a combination of three things. It's Mojo, which is the programming language, the engine, which is the world's fastest unified inference engine, and a serving system to make it easy to deploy into production. Stephen and I work on the engine, and the engine is a drop-in multi-framework replacement for getting a performance boost out of your models. It's extendable with Mojo, and it's general in that you can take it and run it on many types of hardware. In particular, though, Stephen has been doing some awesome work with the rest of the team to make it extensible for your use cases. And really, our goal here is not that you use modular because we can get you performance. It's you use modular because it is a tool that enables you to do everything you want to do. So, Stephen, I've got a simple PyTorch model here. Of course, I don't want to share my model with you, but let's say this is fairly representative of a small test case. It's got a multiplication, a cumulative sum, and a ReLU. I've converted it into Torch script, and I've loaded it into Netron, which is on the right here. So you can see that input coming in, the multiply, the cumulative sum, and the ReLU. I'd like to ask you, what can I do to take this model and make it run faster?
Sure. Well, in normal PyTorch, since PyTorch 2, they have Torch compile. And so if we run that model through Torch compile, you get this output. So in PyTorch compile, there's some flags you can set that will show you what it's doing. And so this is what it produces under the hood. And what you can see is there's three calls here, and each one is called to the kernel in the operation. So we have a multiply, there's a multiply kernel here, there's a cumulative sum here. And so what this means is it means that PyTorch 2 out of the box doesn't fuse this model. Now we're not saying PyTorch 2 doesn't do any fusion. We love PyTorch, we love PyTorch 2, it does do fusion. But this is just to illustrate that if you take a kernel, it's not general enough to expose fusion in PyTorch. And just for full disclosure, you can see here, this is the code on the top, which is for the multiply, which is a specialized kernel, which means they've optimized in the sizes, but it's still not fused. So you still have three kernel calls. So that's not great for Torch compile.
Yeah, so if Torch compile doesn't help me get more performance on this model, what else can I do?
So another option is you can write a custom op in PyTorch. And so here we've written a cumulative sum in PyTorch, and this is specialized on float. So if you want to specialize on other types, you still have to stamp out a new kernel for each type you want to support, and it has to be written in C++. So to write a custom op, you write the C++ kernel, you use their special macro mechanisms which register it with the PyTorch dispatch system, and so when you call it from Python, you go into Python, you go into C++, you go into the dispatcher, which will then call back into your kernel, and then it goes all the way back out. But that's all you're doing by doing this. So you're registering it as this thing, and then you're building it into a shared library, which means you have to invoke the C++ compiler, create this library, which isn't ideal. And after you do all that, you still don't get fusion or graph optimizations. It's just an eager mode kernel. So that's not great either. And this here is the assembly produced if you disassemble the shared library, which I appreciate is not the most relatable thing to do. But if you look at the assembly, this here is the assembly for that kernel, and this is 64 kilobytes, just for that tiny kernel that I had on the previous slide. And if you do -O, then you get a megabyte. So it's a huge amount of assembly for something that doesn't really compose with the rest of the stack.
So Stephen, I did my my education in applied math and physics. I'm coming at this from a data science perspective. I don't really understand all the assembly, but that doesn't seem like a good thing to get out of the program.
No, so
yeah, let's talk about bringing it into Max instead. This is that PyTorch model that we mentioned earlier. To pull into Max, all I need to do is convert it to Torch script, just like I did to view it in Neutron, and then load it into the inference engine. This particular API here is the Mojo-based API for the inference engine, but there are also C and Python versions you could use if you prefer. So, well, coming at it from more of a data science perspective, I'd like to visualize the model and see what Max is giving me. If I do that, I can run this command here, and that gives me this particular graph in Neutron. I can see that the multiplication coming in is happening in Max, but then I'm converting Max tensors back into PyTorch tensors and running the cumulative sum with torch.a10.cumsum, which is great because the model works, even if Max doesn't support that operation. But it's not so great in that I'm guessing I can't do much performance across that boundary, right?
Right. So, I mean, this is a compatibility feature. It means that any PyTorch kernel is still supported in Max because we can convert into PyTorch, run the kernel, and convert back. And we still get all of our optimizations on our stack, and we can do some optimizations in this, but not much because we have to respect the PyTorch API.
All right. Well, if I'm a data scientist and I'm trying to make that work and get it as fast as possible for my model, I don't really want to deal with the PyTorch because you showed me all those slides before. What else can I do here?
Right. Oh, yeah, we forgot about that. But what you can do is you can write a Mojo kernel. And so here is a Mojo kernel, which is exactly the same as the C++ I wrote. It's actually shorter than the C++ I wrote. And it's not specialized on type. So the C++ one was only float. This works for any type. And basically, the whole kernel and everything to do with the kernel is in Mojo. So this is it. There's not some extra thing we're not showing you, which is like a new registration thing or a new thing. This is all you need to do to register a Mojo that overloads a PyTorch operation. Under the hood, PyTorch uses this thing called A10, and that's why it says A10. But this is the PyTorch cumulative sum being overridden. And single source of truth, it's all in Mojo. There's no C++ linker, no C++ compiler to deal with. It's very easy. It builds very fast, and the PyTorch custom op actually takes several seconds just to build, whereas this is much, much faster. And just by writing this, you get the fusion and graph optimizations for free. So it integrates with the full stack of optimizations. The other one was just a kernel that we then call into, but it doesn't integrate with the rest of the optimization stack.
So Stephen, this looks a lot like the C++ to me in that I'm allocating an empty tensor, and then I'm running through it, and I'm returning that tensor. If I'm allocating inside my kernel, how do you do fusion?
Right. So this is something that you may have noticed in the PyTorch. There's this concept of buffer semantic operations where you just take in basically pointers instead of tensors. And most of the frameworks and compiler stacks require that users write a shape thing and a buffer thing. And they will then optimize on the shape and they will optimize on the buffer, but the user still has to have two sources of truth. In Mojo, you don't have to do that. You just have your single source of truth, which is written like a normal PyTorch kernel. And from that, we're able to extract out the shape and extract out the buffer representation. And you don't need to do this. So we're still able to optimize the shape, and we're still able to optimize the buffer. And we do a whole stack of memory optimizations in the buffer, like emplacing or pulling memory. We don't want to reveal all of our secret sauce, but there's a lot of optimizations we can do in the buffers, and we can even do optimizations on the shapes as well. But again, it comes from that single kernel that we showed you, which is just one thing.
All right, so how can I use this?
Right, so you just run the normal Mojo package command. You just do Mojo package, the name of your Mojo file, and you will produce a platform-independent package. In PyTorch, we had a C++ shared library file. That needs to be built on every platform, right? And then you need to include it in your Python for every platform, and you need to have some logic in Python that says, oh, hey, I'm on this platform to include this file. or however you want to package it. And this is platform independent. So you just do Mojo package, get the thing, and then you just provide the path to the previous API that we showed. So you just add this file as a package, and that's it, you're done. It will overload the Python automatically. Yeah.
OK, can you prove that to me? Like, how do I know that Max is actually replacing it here?
Yeah, so now if we do the visualization, before we had a constant and a multiply, and when they came in, they got converted via the PyTorch functions to go into Torch, and then we called the Torch kernel. Now it's all just native Mojo or Max. So there's no conversion, which means we can optimize and fuse and do all of our optimizations on this with just that one kernel.
I see it still says torch.a10.qmsum up there.
Right, so that's how we know what to overload. In PyTorch, each operation has a name like that, and basically what we can do is we can say, well, if you register an operation with that name, then we will call, or you will replace the operation with your kernel instead of the PyTorch thing. And this is the same way as their PyTorch dispatch table works, right? The dispatch table is just adding that name into the dispatch table with a call back to the PyTorch custom op. So it's a very similar way to the way that PyTorch works.
Awesome. That's really cool. Can you go in a little more about those optimizations you mentioned earlier?
Sure. So we take this kernel. We'll do a whole bunch of graph level optimizations. Like I said, we split it into the shape and the buffers, and we can do optimizations in that. But what's also really profound, I think, is that this kernel is fusible. So we can fuse into this kernel, even though if you look here, the word fusion doesn't appear on this slide. Nowhere in that code has the user said, oh, yeah, hey, I want fusion. You can opt out of fusion, but we're able to generically enable fusion for all of the kernels. And just one thing to note, this is also written assuming it's fully static, assuming it's fully dynamic, i.e. we don't know any shape, we don't know any stride. But what happens is we're able to specialize on the fly and specialize for a specific shape if that shape is encountered in a model. And just to show you, this is the assembly produced, right? And this isn't the assembly for the cumulative sum. This is the assembly for the entire model, right? So the entire model has become 17 lines of assembly. And compare this to the cumulative sum, which was 64,000 bytes, right? You can count the number of bytes we have here. So it's really tiny. And the multiply and the cumulative sum have actually become a single instruction assembly, fuse, multiply, add. So I mean, the multiply is now essentially free, like completely free. And there's only one kernel launch, whereas in Torch compile, we showed that it had 3 kernel launches. In this, there's only a single kernel launch, and the entire thing is in here. And then there's the ReLU. So the ReLU is just one instruction as well. So this is like a really tiny amount of code, and you compare it to what we showed with with just the cumulative sum for just float, right? And this is our generic kernel that works with anything. And this works because we've specialized it on the fly for a specific size. I think in this case it was like 1 by 10. But the point is that if you have a model that has that size, you'll get the most optimal kernel for that size. And for free, you didn't really need to do any template meta programming inside of the kernel to enable this. And yeah, and so the reason the assembly is better is 1, there's fusion. 2, there's the static shape information that we're able to propagate and specialize the kernel on. But I mean, fundamentally, it's just this key point, right? Which is Mojo is built on the principle of zero cost abstractions. You don't pay for what you don't use. And so you have ultimate control at the kernel level. You can opt out of the fusion stuff, and you're not going, if you don't, for whatever reason, you don't want that, you don't have to have it. But when you if you are opted into it, you get it for free. And we try and do everything at compile time, and so we are able to generate, these tiny kernels for these special cases. And yeah, just to emphasize, this isn't just our kernels, this is your kernels. Right.
Yeah. Okay, so let's talk a little bit more about the full package story here. So.
Yep, so this is the PyTorch build process. We have the C++ kernel. We have this C++ kernel is taken and compiled via CMake, and you launch the CMake using the CMake command, which then itself launches Python and finds the path to torch on your system and then propagates that to the C++ compiler, which then gives it to the linker, which then includes torch, and then builds this thing. And then finally, once you build it, you have a platform-specific binary, which you can then include in Python, versus you just write the kernel, right? And that's all you do to write the kernel. There's no CMake, there's no, well, I guess there can be Python if you want to use it in Python, but that's all you need to do to register the kernel, and it's platform independent, and it just works, and it gets all the optimizations and things.
All right, so Stephen, I know lots of people who love Python, and I know lots of people who love Mojo. I even know a few people who love C++. I don't know anyone who loves CMake.
No one likes CMake.
So this is really cool, but I've been doing ML for a while, and I started learning this stuff back in the days of Theano and TensorFlow 0.6. Can I do this with anything but PyTorch?
Yep. So this works on any platform that we support in Max. And so we also have the TensorFlow kernel. And this is the same kernel. It's just slightly different, which I'll go into in 1 second. But on this, I just want to say that all of the frameworks we support, you can register a kernel for, and it will overload that kernel. And so it's not just a PyTorch thing or a TensorFlow thing. It works for either. And just to emphasize the differences here, TensorFlow has some attributes in the operation: reverse, which means start from the end, and exclusive, which basically means skip the first one. And those are what TensorFlow calls attributes, which means they're known at compile time. And because they're known at compile time, it means they're parameters in Mojo. So you can see at the top there, reverse bool equals false. That's just saying this is a compile time value, and it means that this all gets specialized at compile time. So you still get the same assembly for the PyTorch one because it has false and false. But if you specialize the TensorFlow one, you'll then get the specialized kernel for true and true, or true and false, whatever. And it's all validated at compile time. So the code that comes out is still very sleek, and the user is the one that parameterized it, essentially, through writing this. And this is the real magic, is that the same kernel can be used as a source of truth for 3 frameworks. TensorFlow, Onyx, PyTorch, all use this one kernel, right? And that's really profound when you think about it, because if you look under the hood of what's going on in these frameworks, they have multiple implementations within the framework of the same kernel. Whereas here, we just have one kernel that's for 3 frameworks. So it's like a pretty big improvement, I think. And yeah, it gives you superpowers.
All right, so something we want to emphasize here is that all of the kernels for all of the models we show on our dashboards, on our performance comparisons, are written in Mojo. But more importantly, they interact with the system the same way your kernels do, in that this registration mechanism, all of the optimizations we've been talking about, are how we get performance out of the system, and we want to give that to you. We don't want to take control away from your dev team. We want to give it superpowers. Why should you care? We picked a random model from our public domain. For a particular Skylake instance, TensorFlow 2.13 on GPT gets 10.2 QPS. This is using the tool to benchmark the same TensorFlow file in Max. You can see easily a 3x speed up. But more importantly, it's not just bigger models. Stephen, you want to take the next one?
So on the left, we have GPT-2, which is essentially millisecond scale performance model, right? So the TensorFlow runs in 100 milliseconds. And what we have here is a real external user who came to us with a real problem they have in their production system. And they have a production baseline that's measured in microseconds. And so around about 50 microseconds. So this is like orders of magnitude smaller than the TensorFlow. And with the same kernels and the same software stack, without any additional compiler flags, we're able to specialize in this case and beat their production baseline, which uses an existing framework that has a whole bunch of custom flags and tuning and all of this stuff, whereas this is the exact same compiler flag in both cases, for both millisecond scale and microsecond scale. So this scales all the way down. And so to be clear, we're not saying we're running GPT-2 in 50 microseconds. We're saying this is a model that is on the scale in a production environment that is a small model, and most of the frameworks just make a mess of it and run it in very, very, they make a mess of it.
Okay. So to summarize, Max gives you state-of-the-art, out-of-the-box performance. You can take your model into the framework. You can execute it. Because of those fallback ops we mentioned, you get coverage. Things work, which is awesome. If you find something that doesn't work for your case, you've got a custom op in your model, Modular hasn't happened to implement that thing for you yet, you've got full pipeline extensibility. You can hook into the same tools that we use to make things fast and use them yourself. It's hardware portable. Like we said, the Mojo kernels spread across different CPUs. We've talked about GPUs this morning, which are coming using very similar APIs, depending on how deep you want to go into your optimizations. And Mojo gives you superpowers. So thank you. And do you have any questions for us?